Look, if you've ever opened a math textbook to the chapter on arithmetic progressions, seen that massive wall of confusing letters, and just felt your heart sink, well, you are absolutely in the right place. Today, we're completely bypassing those traditional memorization traps. I'm going to show you a smooth, gap-free framework that'll help you master arithmetic progressions using just a simple 3-word trick. Let's just dive right into this. You know, they always say your brain stores stories, not formulas. And honestly, it's so true. So many students beat themselves up over blanking on math equations during an exam, but hey, it's not your fault. It's a proven fact that isolated formulas just kind of vanish under pressure. Your brain literally isn't hardwired to remember a random string of algebraic characters without any real context, but it is perfectly designed to remember a logical sequence of events.
And that brings us to the core of this explainer. Instead of that super intimidating standard formula, you know the one, a sub n equals a plus n minus 1 times d, we are swapping out all those scary math letters for a continuous logical 3-word chain. Start, step, sum. This right here is our smooth, gap-free solution to really understanding arithmetic progressions. Instead of blindly reciting a formula, you're just going to tell yourself a very short, very logical story.
To make this stick forever, let's anchor the concept with a real-world story. Picture a simple staircase, or maybe a salary ladder. Say Reena gets a job with a starting salary of 8,000 rupees, and every single year, her salary goes up by exactly 500 rupees. So year 1 is 8,000, year 2 is 8,500, year 3 is 9,000. You get the idea. An arithmetic progression is literally just that, a repeating pattern of equal jumps. That's the whole shebang. So let's break down our 3 magical words, starting with the first one, start. This is incredibly straightforward, right? Start is exactly what it sounds like. It's where your sequence literally begins. Going back to our staircase visualization, the start is just the very bottom step. Or, for Reena's salary, it's that initial 8,000 rupees. In standard math terms, this is simply what your textbook calls the first term. Moving on to our second word, step, which, by the way, you can totally think of as a jump. This is the fixed, equal amount added every single time you move forward in the sequence. Now, the absolute golden rule here is that this jump has to be constant. If you're climbing stairs, every single stair must be the exact same height. If the height changes, well, you're going to trip. And mathematically, it's no longer an arithmetic progression. It has to be a fixed difference. Finally, our third word is sum, which we often swap out with count, depending on what the problem is actually asking us for. This word represents exactly how many steps you want to take in total, or the total accumulated height you've climbed over a set period. Think of it as the ultimate destination of your math story. Where exactly are we going, and how much have we gathered along the way? By using this kind of anchor mapping technique, we can seamlessly bridge our simple English words straight to the math variables your teacher uses. So start perfectly maps to A. Step maps perfectly to D, the common difference, and sum or count maps right onto N or S sub N. By doing this, we completely wipe out the friction of learning new, confusing symbols. You're literally just translating a story you already intuitively understand into the language of math. Okay, let's see how this builds into actual formula derivation without any rote memorization. Imagine you're standing at the bottom of our staircase, and you want to reach the 5th step. Think about the physical logic here. You don't take 5 jumps to reach the 5th step from the ground, right? No, you take 4 jumps. To reach the 100th step, you take 99 jumps. You always take one less jump than the step you're aiming for. And when we translate that undeniable physical logic into our framework, we get this beautifully simple equation. Your future term equals your start, plus the number of jumps, which is n minus 1, multiplied by the size of your step. Look at that. You just built the famous nth term formula entirely on your own. You've substituted rote memory with genuine foundational understanding. How cool is that? But hey, before we apply this, I need to flash a quick warning sign. The absolute most common exam mistake students make globally is forgetting this physical logic. In a panic, they multiply the step by the full count instead of subtracting 1. Always remember the staircase. If you want the 20th step, you are only taking 19 jumps from your starting position. Lock that visual in, and I promise you, you will never make this mistake again. All right, let's move into section 1, real exam problems solved in 3 words. Here's our first problem, a classic easy level sequence. Find the 15th term of 3, 7, 11, 15. First off, don't panic. Just find our three words. What's our start? Well, it's clearly 3. What's our step? To go from 3 to 7 and 7 to 11, we're adding 4 every single time, so our step is plus 4. And our count. We're looking for the 15th term, so the count is 15. Easy, right? So let's map out the final answer using our physical logic. We start at 3. To get to the 15th term, we need to take 14 jumps. Each jump is worth 4. So 14 multiplied by 4 is 56. We add that to our starting point of 3, and boom, we land directly, smoothly on 59. No messy algebra required, just pure logic. Honestly, you can do this in 10 seconds flat once you get the hang of it. Let's dial up the difficulty a bit to a medium-level problem. Which term of 5, 8, 11 is 50? This time around, they're giving us the final destination, but they're asking for the count. So, we know our start is 5. We can clearly see our step is plus 3, and our target landing spot is 50. So let's just work backward with a tiny bit of quick algebra. If we landed on 50 and we started at 5, that means we covered 45 units of distance through jumping. If every jump is 3 units long, 45 divided by 3 means we took exactly 15 jumps. And remember our golden rule? The term number is always one more than the number of jumps. 15 jumps means we landed on the 16th term, so the answer is 16.
Now for a real-world word problem. A student saves 5 rupees, then 8, then 11 each week. What is the total saved in 10 weeks? Notice that keyword total. This signals we need the sum concept. Our start is 5, our step is an extra 3 rupees a week, and our count is 10 weeks.
Using the sum formula, powered by our 3 simple words, which essentially calculates the average of the first and last term multiplied by the count, we can find out exactly how much was accumulated. Through the seamless translation of our start, step, and count right into the sum equation, we arrive perfectly at 18.5 rupees. It's a real-world problem, completely solved just by identifying those core story elements. Okay, I want to pull back for a second and look at the broader picture of this entire chapter, because it really boils down to a 4-word compression engine. Add same number repeatedly. No matter how complicated an arithmetic progression problem seems on the surface, whether it's about salaries, falling objects, or savings accounts, at its absolute heart, it is literally just adding the same number repeatedly. If you understand that, you own this entire topic. So as we wrap up this explainer, I want you to mentally lock in this 3-word chain one last time. Just store it right now in your memory palace. Start, step, sum. Say it to yourself. The next time you sit down for an exam, don't try to pull complex formulas out of thin air. Just quickly write down these 3 words at the top of your paper and watch how easily the math just flows right out of them. You've just seen firsthand how a simple visual framework can completely eliminate math anxiety and replace rote memorization with true, gap-free understanding. But man, it really makes you wonder, if 3 simple words can unlock arithmetic progressions forever, what could an incredibly powerful 4-word chain do to completely demystify quadratic equations? Keep that thought in mind, keep learning efficiently, and I will see you in the next explainer.